All right, so this is the first lesson from the last unit of the course. Now, this unit, which is focusing on what we call exponential functions, and it starts off with looking at geometric sequences in series. Now, this is something that used to be part of the Pre-Calculus 11 course, so you may have learned this before, at least the first parts, but if you have, we'll definitely go more in depth than you would have. But I want to start with what a sequence is. And actually, going back to grade 10, you would have learned about an arithmetic sequence. It's a relatively small part of the course, but now I want to look at a geometric sequence. Now, first, just a sequence, just the word sequence in mathematics just means a list of numbers. There's always, it's a discrete list of numbers, and sometimes it goes on forever, like this pattern here goes on forever, insinuated by the ellipses there. Or sometimes it has a finite number of terms. It comes to a stop. There's always a first term, and the first term we call T1, or sometimes A, but the textbook uses T1, so I'll use that. And then that's the first term. There is no zeroth term. There is no negative terms. We always, by convention, start with term 1. So this would be term 2. This is the third term. 54 is the fourth term, and so on. So what makes a geometric sequence? A geometric sequence is a series of numbers, in which the pattern is always described by multiplying some constant number to a term to get to the next. So for example, in this sequence, hopefully you've noticed by now that to go from 1 to the next, I'm multiplying by 3 every single time. If it wasn't the same every time, then it wouldn't be an arithmetic sequence. And as long as you were multiplying by some common value every single time, it's a geometric sequence. So it's a pretty simple sort of pattern. And that value, in this case it's 3, is what we call the common ratio. So the common ratio, which we usually just denote with the variable r, is the value you are multiplying by each time. Keep in mind, if you're multiplying by a number between 0 and 1, your values will get smaller every time, right? If you're multiplying by a half, it looks like you're dividing by 2 every time, because multiplying by a half is equivalent to dividing by 2. If you're multiplying by a negative, your signs will switch. The signs of your terms will switch back and forth between positive and negative. But to be a geometric sequence, this must be a constant value. This r must always be the same. So I'll say this must be a constant value. So like I said, if you're multiplying by 3 the first time and then 2 and then 1, I'm not saying there's no pattern, but it's not a geometric sequence. All right, and in general, if something is a geometric sequence, we can always summarize the pattern with the relationship between the term and the term number. And again, if I look at this simple example at the top, 54 is the term, 4 is the term number, or 2 is the term, 1 is the term number, right? We always want to be distinguished between the term number, in this case, the first, second, third, fourth, and so on, and the actual term, in this case, 2, 6, 18, 54. And if it is a geometric sequence, this equation here will always relate the term number to the term. And so in this case, n again is the term number, r is the common ratio. In fact, I'll be consistent and highlight that in green. And T1 is the first term. And so we'll use this in a moment, but in general, all this really means, if you want to find any term of a geometric sequence, all you need to do is find the first term and multiply by the common ratio a number of times. How many times? 1 less than the term number. And so let's look at this. Let's look at this sequence right. Well, actually, how about this? For the example, maybe I'll use an example for above. So for the example above here, I can say this. If I want to find any term of this sequence, I can say any term can be found by the first term times the common ratio, 3, to the power of the number of terms, the term number I want to find. Let's say I want to find the 15th term. I want to raise to the power of 15, take away 1. And why take away 1? Well, notice, let's say I want to look at term 4, 54. Compared to term 1, to get from term 1 to term 4, I have to multiply by 3 times, not 4 times, right? It's the 4th term, but to get from term 1 to term 4, I have to multiply by 3 times. If I want to get to term 5, whatever that number is, I would have to go back to term 1, or one way of looking at it is go back to term 1 and multiply by 3, 1, 2, 3, 4 times. Always 1 less than the term number. All right, so with that said, let's look at this. So let T1 equals 2, T5 equals 162, find T2, T3, and T4. The main thing about this is understanding the notation. So if we understand the notation, this becomes relatively quick, although there's still some aspects we have to, that may be a bit challenging. So first, T1, that's the first term. T5 is the 5th term, and I'm trying to find the terms in between. Okay, so what I would generally recommend, especially if we're choosing to focus on a sequence, I would kind of lay out a structure of, in this case, my 5 terms. I have 5 terms here. T1 we know, T5 we know. So we know those two. We don't know the ones in between. That's what we're trying to figure out. T2, I should say. T3 and T4. And we know this is a geometric sequence. And now, to be honest, I don't actually say here it's a geometric sequence, but now I'm just saying this is a geometric sequence. Now, if I didn't say that, then it's not possible to know these middle terms. I mean, it could be literally anything. But we know it's a geometric sequence, so we know that every time to go from here to here, we have to multiply by this same number. I'll call it R to be uncreative. And eventually, that would lead us to 162. Now, what I recommend against is immediately going back to this formula. There's a few formulas in this unit, and like any formula, if you just always by default go to it, you're not thinking, you're just being robotic, and you are rarely actually making your life easier. So I may want to use that, but I highly recommend against just always jumping to a formula. In this case, I'm not going to use one to find these middle terms, and that's because the main thing here is I want to figure out this common ratio. And I don't need a formula to figure out. I can just literally see that if I take 2 and multiply by R 1, 2, 3, 4 times, it'll equal 162. So why don't I just write that down? If I take 2 and multiply by R 4 times, I know that must equal 162. Which means I must be able to solve this. And so let's solve for R. Because once I know R, then once I know my common ratio, it's quite easy for me to find these middle terms. So how would I solve this? Well, I would divide both sides by 2. So R to the power of 4 equals 81. And then I need to find the 4th root of both sides. So R will equal the square root, the 4th root of 81. But because I have an even numbered power here, then I know there's going to be 2 possibilities, plus or minus. Every time, same thing with a power of 2. When you square root both sides, there's 2 possibilities. Same thing for a 4th, power 4, a power 6, anything that's even. That said, the 4th root of 81 is actually a nice number. It's exactly 3. And so that means the common ratio must be either plus or minus 3. So there's 2 possibilities for my common ratio, which means some of my terms have more than one possibility, but not all of them. What do I mean by that? Well, let's see. Let's say R is positive. Okay. Let's say R is positive 3. Well, then my second term will equal 2 times 3, which is 6. My third term will be 6 times 3, which is 18. And my 4th term will be 18 times 3, which is 54. And if I multiply by 3 again, I get to 162. Or what if R is negative 3? Well, then my second term would be 2 times negative 3, which is negative 6. My third term would still be positive, because negative 6 times negative 3 is positive 18. And my 4th term would be negative 54. And then my 5th term, again, would be the same thing that you were given. So there's 2 possibilities here. Notice in the end, I didn't use my formula from before. In the end, I had to find a fourth root of both sides, but not a lot of algebraic work here. And I never want us to lose sight of the fact that if we're dealing with a geometric sequence, which we are for the next few lessons, then there's always I'll say, a simple pattern. And I say that knowing that it's always going to be just some number repeatedly being multiplied. Once you know that number, there's not much more to it. And I don't want to think that these formulas are always going to be helpful. For something like this, I think this was by far the most useful way of approaching it. All right, let's look at this. Find the number of terms in this geometric sequence. So what do I have here? I have 32, that's my first term. So I'll call it T1. 64 is my second term. So T2. Then I skip a number of terms, and I end up with 16,384. That is term I don't know. I'm trying to figure out. So I'll call that Tn. I'm trying to figure out n. So in this case, that formula, that sort of general term I gave us at the beginning is quite useful because I have all the sort of structure of all the parts that I need right here. And so that equation was this, Tn equals T1 times r to the power of n minus 1. So notice if I look at this, I know my first term. I know what the last term equals. I just don't know the term number. The common ratio, I'll know in a second. I can just see the common ratio must be 2. And so I know r as well. And so I can now quickly use this and say, instead of Tn, I can say 16,384. The first term is 32. The common ratio is 2. Oh, let's try that again. 2. And I don't know what n is. Okay, so now I want to solve for this. So what would I do? Well, first, let's isolate the power. So let's divide both sides by 32. Calculator's helpful here. 16,384 divided by 32 is 512. On this side, I have 2 to the power of n minus 1. Now, here's where things get a bit tricky. This n we see here is in the exponent. And how do you solve an equation where your variable is in the exponent? So n is in the exponent. So how do you solve an equation with a variable in the exponent? Well, you haven't really done this much before. So if it feels familiar, you probably shouldn't, unless you've taken parts of this course before. Because really, you have two options to solve this. To solve when you have a variable in the exponent. One is by inspection. So I'll say to solve either by inspection, which means kind of look at it and essentially like it's a guess and check. Just kind of look at it and try to figure out, okay, 2 to the power of what will equal 512, or 2 to the power of what, take away 1. If you don't like that, your other option is by using logarithms, which we will get to at the end of the unit. That's the last third of this unit. So until we learn about logarithms, and we can't understand logarithms properly until we know what exponential functions are. And we can't really, we're basically leading into that right now. So long story short, it's going to be a little while until we actually can solve this algebraically, until I expect us to. That said, it's actually not hard to solve this by inspection. Really, I got to think about 2 to the power of what equals 512. And it shouldn't take you too long to do a bit of guess and check. And you should find out that 2 to the power of 9 equals 512. So that means that all of this here is 9. That means that n minus 1, not n, equals 9. So that n must be 10. And again, it really shouldn't take us more than, 30 seconds to figure out that 2 to the power of 9 is 512. And so I will say, though, until we learn about logarithms properly, I'm not going to expect anyone to be solving things using logarithms. And you want to be wary. If you learn it before I talk about it, sometimes we learn steps, but we don't know why it works. And clearly, I'm never a big fan of that. But notice, that wasn't actually so hard. Okay, just a little bit of guess and check, essentially. Okay, let's look at this. What I have now are the first 5 terms of a geometric sequence visualized as a graph. And you can see I have term number in the bottom. So again, this is term number 1, term number 2, and so on. What I want to know is I want to determine the value of T10 as accurately as possible. So T10 is over here. There's a 10th term. So what is that term as accurately as possible? I say that because it's hard to know exactly where all these points are. First, though, what I would recommend is thinking about, I see it. What sort of shape do I see here? Can I generalize the pattern visually? And so first, I'm kind of connecting the dots. But what do we think happens next? If we're not sure, fair enough. I'll just kind of pause right here. But what happens as we go this way? If we can visualize that, we can start to immediately get a rough guess for what 10 is. But I want to be a bit more accurate than that. So I'm going to pause this there and think about, OK, I'm trying to find the 10th term. What do I know right now? Well, I know the first term sure looks like it's 200. So I'm going to focus on the first few terms that we have here. So term 1 definitely looks like it's 200. What about term 2? Let's look at my graph. Term 2 looks like it's at about 130. If it's not 130, it's extremely close. So that looks like 130. And that's really all I need to focus on. Term 3, if I look at that one, which I've highlighted in blue, it looks like that's about there, about what, 84, 85-ish. That said, I'll put that down there. But really, I need to figure out the common ratio. And I just need to look at one pair of numbers in a row to figure out or one pair of terms in a row, I should say, to figure out the common ratio. And I already got that right here. So from here to here, I can figure out my R. And so what's that going to be? 200 times what equals 130? Well, I don't know. Pretty easy to figure it out, though. 200 times what equals 130? That's the same as 130 divided by 200, which comes to 0.65. And so my common ratio seems to be about 0.65. If it's not 0.65, I know it's very, very, very close. And again, if I just take 130 and multiply by 0.65, I get about 84.5. So, I feel very, very confident about this common ratio of 0.65. So now that I know my common ratio and I know my first term, I can find the 10th term really quickly. So I can now say, OK, so if I want to find the 10th term, let's go back to this. Any term can be found by the first term times the common ratio to the power of n minus 1. In this case, I want to find the 10th term. It's going to be the same as the first term, which is 200, times the common ratio, which I said is 0.65, to the power of, I know the term number, it's 10 take away 1. That's it. I can type everything on the right into my calculator, and you get about 4.14. So that's my 10th term. And that, like I said, the only reason that may, besides rounding, like I said, I may not be exactly sure about the values of the first and second terms. But like I said, if they're not exactly 200 and 130, they're extremely close. Those points seem to be right on it. So notice, if I go back to my graph now, the 10th term is about 4, so I can visualize that roughly about right there. And so perhaps now you can kind of see the sort of visual of what happens as we keep going on. And that's a sort of visual of how this geometric sequence behaves. Now this shape here is actually a type of exponential function, and that's what the next chapter is focusing on. We call this exponential decay, this sort of shape of the curve. But really right now, this is more sort of a lead-in. Looking at graphs is really going to become something we'll look at in later lessons. All right, last question, final problem. I talk about a depreciating asset. Depreciating means it gets loses its value over time, as opposed to appreciating. Appreciating is some sort of investment or asset that gets more valuable over time. For example, generally real estate, especially in this city, generally over time, real estate gets more and more valuable, whereas cars are the opposite. There's very few exceptions. Cars get less valuable over time. And they can generally be modeled quite accurately with a geometric sequence. Okay, so what I have now here is two prices for two different models of the same car, Tesla Model S. So I have a 2014 model for about 59,800, and I have a 2015 model for 69,300. I want to use just this to make a prediction of what a 2019 model would cost. Okay? So how can I do this? Well, first I need to think, how can I set this up like a geometric sequence? What I'm going to do, and I always have choices, I'm going to call this term 1, I'm going to call this term 2. And so term 1, term 2. But I want to remind myself that term 1 is the 2014 model, term 2 is a 2015 model. I'm trying to find the 2019 model, so that would be 2016, 2017, 2018, 2019. So I'm trying to figure out this term right here, which is term 6. Okay, and so once I especially write my values in here, you can see how more and more I can just bring this back to this previous sort of questions we've looked at. My first term is 59,800. My second term is 69,300. What is this term here? And now I have this sort of structure that should look familiar. If I want to find the sixth term, I need to find first the common ratio. So what's the common ratio for all of these? Well, I need to look at two terms, which I have. And so the common ratio, essentially the idea is, 59,800 times what equals 69,300? Well, I don't know, but again, I can figure it out quite quickly by going 69,300 divided by 59,800. Go to a calculator, you get about 1.16. That's my common ratio, which means one way of looking at it is your car gains 16% in value for every year, every newer year that it is. Okay, because we're kind of looking at time kind of backwards here. As our terms get larger, we're going forwards in time. But again, you may also, you could set this up going the other way around. But that's it. I think I'm just confusing you now, so I'm going to shut up. And so with that said, I got my common ratio. And so let's now go back to my general form for a geometric sequence. And again, I'm trying to find the sixth term. I know the first term. I know the common ratio. Oh, got an announcement.
Sandra, can you please contact local 2222? Yes, Sandra, local 2222. Thank you.
And so in a moment, we'll know the sixth term. Just type that into my calculator, and you get about $125,000. Now, I will say, when I made this problem, it was the year 2019, and that was quite accurate. Now that it's a later year, because this car would have depreciated, this is no longer so accurate. Because again, cars keep getting less valuable over time. But at the time, when I made this question in 2019, this, just by having this two little bits of data, it was actually extremely accurate for what this would cost in Canadian dollars. Okay, so my last question though, which again is really easy if you understand what all this means. And again, the more we focus on formulas, the less you probably understand what these things mean. The last question is, say you wanted to purchase a Tesla Model S, the same type of car, for under $50,000. What year should you plan to buy? So how can we figure that out? Again, I'm wary of using formulas. In this case, it will definitely not be more helpful than what I want to say. But what year, what model would that be? So for this, what I would recommend is go back to my equation here and realize I know that as I go this way in time to newer cars, roughly every year the car gets 1.16 times more valuable. So I want to go backwards. Clearly, if I have $50,000, I have to get an older model than a 2014 according to this. So when we go backwards, although in some ways that becomes term 0, and I said by convention we never have that. At the same time, the question never said, that this has to be formed as a geometric sequence. It just said it can be modeled that way. And so even though by convention we don't have a term 0, I can still go back before the year 2014. And if I want to go this way, that means I want to divide by R. And what I want to do simply is just take my 59,800, divide by 1.16, and according to my model, I could say term 0, but the 2013 model would be $51,551. Not enough. So I got to do that again and go back again, divide by r again. And so I'll take that number, divide by 1.16 again, and not surprisingly, I'm now under 50,000. If I divide by r again, I get about $44,441. So what year is that? That's the 2012 model. And so notice again, I didn't need any formula to do that. I just, once I knew what the common ratio was going this way, well, going this way, I'm going to divide by that number. And so again, the answer to this, according to this, you should be about a 2012 model. Okay, so before I finish this, really, 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 please take my advice of using formulas sometimes, but not automatically. So many of these questions, like that last one, like trying to find the 2012 model, would be so much more difficult if we just immediately jump to an equation, replace a term with 50,000, and try to solve backwards, making it so much more difficult. Okay, in its essence, a geometric sequence is quite simple, just multiplying by the same number over and over. We don't want to lose sight of that simplicity. And now I shall be quiet.